Hello and welcome back to my Amateur Radio General Class License course. It's a wonderful day in the amateur radio neighborhood. Today we're going to talk about solar activity and how it affects radio waves. I wonder how many people are concerned about the possibility of a coronal mass ejection that's on the scale of what occurred back in 1859, an event that is commonly known as the Carrington event. It created what was perhaps the most powerful geomagnetic storm ever recorded. They say that you could see the northern lights as far south as the equator. It's calculated that if such an event were to happen today, it would cost the United States alone up to $3 trillion or more in loss of electrical infrastructure, supply chains, communication systems, satellites, and so on. Such an event is inevitable, believe it or not, but the risk of it happening at any given moment is extremely low, and this rates this particular boogeyman event at a high impact yet low probability in terms of emergency management. And while the Carrington event is like the tsunami, normal solar activity is more like high tides and low tides. So as we progress, as we progress through the 11-year solar cycle, our ability to use certain bands wax and wane. So today, as of this recording, we're at solar minimum, which is part of the solar cycle where there's fewer sunspots. And this makes bands like 10 meters and 6 meters for that part difficult to use. And during peak cycles, those bands can really hop. So today we're going to cover the significance of solar activity and how it affects radio communications. Are you ready to learn? Let's get started. This is the Amateur Radio General Class License Course, Lesson 3. I'm your instructor, Gary Stevens, Kilo Echo 2 Golf Sierra, that's KE2GS. This covers subelement G3, which is radio wave propagation. There are 3 exam questions out of these 3 groups. And this pool of questions comes from the 2019 to 2023 General Class FCC Element 3 question pool, which went into effect July 1st, 2019. Again, this section we're talking about radio wave propagation. In particular, we're going to be discussing sunspots and solar radiation, ionospheric disturbances, propagation forecasting and indices, maximal usable frequencies, lowest usable frequencies, propagation, ionospheric layering or layers, critical angles and frequencies. We're also going to be talking about high frequency scatter, near vertical incidence skywave, and much more. And in this first section, we're going to talk about sunspots, solar radiation, ionospheric disturbances, propagation forecasting, and indices. So a sunspot is a phenomenon that's temporary on the surface of the sun. It's just a region on the surface of the sun that where the temperatures are reduced, and they're believed to be caused by concentrations of high magnetic field or high magnetic flux that just hold the spot in place. For the exam, however, we need to know the significance of a sunspot number with regards to HF propagation. Is the higher the number of sunspots generally indicate the greater probability of good propagation at higher frequencies. A sudden ionospheric disturbance, or SID, is a perturbance of our atmosphere, or in particular the ionosphere, which is generally caused from a solar flare or a coronal mass ejection. What you need to know for the exam is the effect of a sudden ionospheric disturbance that it has on the daytime propagation of radio waves is that it disrupts signals on lower frequencies more than on higher frequencies. When a solar event happens, it takes about 8 minutes for us on Earth to know about it. The speed of light, it takes 8 minutes for the sunlight to reach the Earth, but the particles or the solar wind can take up to 4 days. For the exam, you need to know that it takes approximately 8 minutes for increased ultraviolet and X-ray radiation from the solar flares to affect radio propagation on Earth. And you have to remember that ultraviolet light is light and X-rays is in the light spectrum, so they all travel at the same speed, which is the speed of light. As we touched on earlier, there are certain frequencies that are, just react poorly during periods of low solar activity, which we're in now. So for the exam, you need to know that 15 meters, 12 meters, and 10 meters are least reliable for long-distance communication during periods of low solar activity. Forecasters talk about solar flux. What they mean is the measure of solar radiation at 10.7 centimeters in wavelength. And you need to know that for the examination. Just like the Terryton event we talked about earlier, you need to know for the exam that a geomagnetic storm is a temporary disturbance in the Earth's magnetosphere. I like this particular photo. It shows that the power lines being affected, which during events in the past, telegraph wires have melted and caused fires in telegraph offices and telephone poles. The 20-meter band can be thought of as old reliable. I need to know for the exam that at any point during the solar cycle, you can reliably communicate worldwide during daylight hours on 20 meters. We talked about earlier how the geomagnetic storm could perturb the Earth's ionosphere. This photograph kind of shows it a little bit. You need to know for the exam that degraded high latitude HF propagation is an effect that a geomagnetic storm has on radio propagation. Other than being beautiful, auroras have some interesting effects when it comes to radio propagation. For the exam, you need to know that a benefit of high geomagnetic activity can cause radio communication is that an aurora can reflect VHF signals. That's particularly true on 2 meters and 70 centimeters. Because the sun is on an axis, it appears that the rotation number of days can vary on its surface. For the exam, you need to know that the sun's rotation on its axis causes HF propagations conditions to vary periodically in a roughly 28-day cycle. Yes, so particles are not traveling at the speed of light, so they take a little bit longer to get to Earth. So for the exam, you need to know that it takes 20 to 48 hours for charged particles from a coronal mass ejection to affect radio propagation on Earth. I wonder where all the solar indexes come from. They come from your tax dollars. There's a division of the government, NOAA, which they have a division which is the Space Weather Prediction Center. For the exam, though, you need to know that the K index indicates short-term stability in the Earth's magnetic field. Likewise, you need to know that the A index indicates a long-term stability in the Earth's geomagnetic field. So A is long-term and K is short-term. The charged particles from the sun create all kinds of interference in the HF band. For the exam, you need to know that HF communications are disturbed by the charged particles that reach the Earth from solar corona holes. Takes us to the next section where we're going to talk about maximum usable frequencies, lowest usable frequencies, and propagation itself. You've heard before that the shortest distance between 2 points is a straight line. Radio waves don't always, well, they always go in a straight line, but it may not be in the direction intended. So sometimes it will bounce off the ionosphere and create a short path, but it can go 180 degrees and go all the way around the world, bouncing out on the atmosphere and off of the Earth, which creates a long path. And this is called skywave long path propagation. For the exam, you need to know that the characteristic of the skywave signals arriving at your location from both short path and long path propagation is you might hear a slightly delayed echo, or a slightly delayed echo might be heard. So maximum usable frequency is the highest radio frequency that can be used between 2 points, and it be reflected or off of the ionosphere, or skywaved, or skip as they call it. For the exam, you need to know the factors that affect the maximum usable frequency. And this is path distance and location, the time of day and season, and the solar radiation and ionospheric disturbances. But the answer in the question will be all of these are correct. You may recall, attenuation is just a force or effect that reduces the value of something. For the exam, you need to know when selecting a frequency for the lowest attenuation when transmitting on HF or high frequency is select a frequency just below the maximum usable frequency. A reliable way to determine what the maximum usable frequency is just listening to the beacons. So for the exam, you need to know that a reliable way to determine the maximum usable frequency, particularly between 14 and 30 megahertz, is listening to the signals from the international beacon in the frequency range you plan to use. So in general, all radio waves get bounced back to Earth, but what this question wants to know is what usually happens to radio waves with frequencies below the MUF and above the LUF when they are sent into the ionosphere is they are bent back to the Earth. Exam, you need to know what usually happens to radio waves with frequencies below the LUF is they are completely absorbed by the ionosphere. During certain conditions, lowest usable frequency just may be the one that's the lowest between 2 points. In other words, communications may exist, but if you go higher, it's going to skip further, and you're not going to be able to talk to a particular person in the area you would like to. So for the exam, know that the LUF stands for the lowest usable frequency for communications between 2 points. And likewise, you have a upper limit of distance for versus frequency. So for the exam, you need to know that the MUF stands for the maximum usable frequency for communications between 2 points. So just how far does a radio wave travel on a skip? It depends. But for the exam, you need to know that 2,500 miles is the approximate maximum distance along the Earth's surface that's normally covered in one hop using the F2 region of the ionosphere. We tend to get less mileage out of the E region, however. So for the exam, you need to know that 1,200 miles is the approximate maximum distance along the Earth's surface that is normally covered in one hop using the E region. So what happens if the LUF exceeds the MUF? You don't get a signal. For the exam, you need to know what happens to HF, or high frequency propagation, when the lower usable frequency exceeds the maximum usable frequency. Is no HF radio frequency will support ordinary skywave communications over the path. In this last section, we're going to talk about ionospheric layers, critical angle and frequency, HF scatter, and near vertical incidence skywave. So basically the layers that we're concerned with in the ionosphere are the D, E, and F layers. D, think of it as a daytime layer. So D for daytime, and that way you get it correct. So the test, you need to know the ionospheric layer that's closest to the surface of the Earth is D layer, or the daytime layer. In the previous slide, we saw how the D layer is added during the daytime, and how the F2 and F1 layers combine to one layer at night. So during the day, they're at their maximum thickness. For the exam, you need to know that the Earth's ionospheric layers reach their maximum height where the sun is overhead. This slide shows the F region as one. Imagine that it's split in two, F1 and F2, with F2 being at the top layer. For the exam, you need to know that the F2 region is mainly responsible for the longest distance radio wave propagation because it's the highest in the ionosphere, and that's where we get the maximum distance. Vertical angle refers to where you need to point your beam, or the angle you need to be to get from point A to point B or to point C. For the exam, you need to know that the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions is what is meant by the term critical angle. During the daytime, it's difficult to reach out and touch someone on 40 meters, 60 meters, 80 meters, and 160 meters because the D layer soaks up the radio signals like a sponge. For the exam, you need to know that long-distance communications on 40 meters, 60 meters, 80 meters, 160 meters are more difficult during the day because the D layer absorbs signals at these frequencies during daytime hours. A long time ago, in a place far, far away, I worked for a communications company. It manufactured FBI consoles that used meteor frequency scatter, or meteor scatter, to communicate long distances. For the exam, you need to know that a characteristic of HF scatter is a signal that has a fluttering sound. You also need to know that energy scattered into the skip zone through several different radio paths make high-frequency scatter signals sometimes sound distorted, much like what we talked about earlier, the fluttering sound. Because HF scatter signals do scatter, they kind of go every which way. So you need to know for the exam that HF scatter signals in the skip zone are usually weak because only a small part of the signal energy is scattered into the skip zone. The advantage of scatter is because it is scattered, it's not going past or go into the skip zone, or you're not being jumped over. It's scattered, so it's just dispersed throughout the whole zone. For the exam, you need to know scatter is a type of propagation that allows signal to be heard in the transmitting station skip zone. If you can adjust the elevation on your beam, then you can change the angle in which your signal's taking off from Earth. For the exam, you need to know that a short distance MF or HF propagation using high elevation angles is called near vertical incidence skywave propagation, or NVIS. And as we talked about the D layer earlier, you need to know for the exam that the D layer is the most absorbent of long skip signal during the daylight hours on frequencies below 10 megahertz. So, like I said, it just absorbs it like a sponge. So this concludes Lesson 3. Well, I hope you've enjoyed today's lesson. If you have any questions or comments, please leave them below. And I invite you to subscribe to my channel. This gives you the advantage of knowing when future videos are released or there are any updates. So until next time, never stop learning.